welcome to our webinar this month, and at the outset, a very happy new year to all of you. Before we get started, a few bookkeeping items. The presentation will begin shortly from Bhaven and Sharad. It'll go on until approximately 1 p.m. Bhaven and Sharad have agreed to stay on for a few minutes thereafter to address any questions or dialogue that people may have. The slides and the recording will be available at the end of this presentation. Log into your Millibo account to view them. Please keep your telephone or your microphone muted at all times. Only unmute yourself to ask questions. You can ask questions two ways: one via chat, and second, if you're unmuted, you can ask it directly. For this present webinar, since there are quite a few attendees, I've kept everyone muted except for Bhaven. So please send me your questions, and I will unmute you, at that time. Let's see. For those. Let's see. Other thing, Bhaven wants questions, as you have them, so don't stagger them to the end. Also, this webinar is intended to be, interactive, so please chime in with questions, comments, insights, observations, etc. Let's see. With that, let's go ahead and get started. Today, we are delighted to have Bhaven Avalani and Sharad Murthy to talk with us about eBay's work in developing Pulsar.io, a real-time analytics at-scale platform at eBay. There is considerable interest and work in both academia and industry on big data analytics as well as scalable distributed platforms that can support such analytics. We've had a few talks in the formal category in our previous webinars, and today Bhaven and team will talk with us about what we need to do in the underlying systems and platforms to support analytics at scale. As a side note, by the way, this is our first industry talk. In March, the folks at Microsoft will talk about their efforts in this area, and later in the summer, the folks at Facebook have consented to give a talk as well. So lots of exciting talks and times ahead. Bhaven Avalani is a Senior Director for Platform Services team at eBay. He leads the analytics, monitoring, and storage products at eBay. Large-scale distributed systems are his passion. Prior to eBay, Bhaven has worked on a variety of engineering roles at Adobe, Quintus, and Informix. And for those of you from a few universities, Bhaven and I did a trip to some of the campuses, so you obviously know Bhaven as well. Sharad Murthy is a principal architect at eBay. He has extensive experience in streaming, ESB, graph databases, and distributed systems. And prior to eBay, Sharad has worked at Caspian Networks, Hewlett-Packard, and Fidelity Investments. With that, let me go ahead and turn it over to Sharad and Bhaven. Take it over, guys.
Thank you, Sridhar. Good afternoon, everybody. I'm Bhaven, and I have my colleague Sharad, and we are going to talk about real-time analytics at scale at eBay. So the agenda for today, we have a lot of slides to cover, so we'll move fast, but feel free to stop us and ask us questions. We'll lay down the problem statement by giving some real business use cases and the requirements thereof. There will be a deep dive into the technology that we have built and actually is live in production at eBay, and we are looking at open sourcing it soon, which we use to solve this problem. We will have a demo, and we will leave with some interesting open questions which we are still working on, and we would love to have people participate with us to help us solve those problems. So Pulsar, the code name for this initiative at eBay is Pulsar. It's essentially the real-time analytics platform that we use for a variety of real-time use cases. So the focus here is real-time, and I will kind of expand on it by taking some use cases. So the first use case I want to discuss is behavioral analytics. Google Analytics and Site Catalyst are industry offerings in this area. So this, we have users who interact with eBay across the internet and on their mobile phones and so on. And while they are going through the eBay application, their clicks, impressions, conversions, pinches, and whatever is being collected for us to understand user behavior. And there are a few areas out here where real-time analytics has a significant value proposition. So if we try to look at targeting in session. So while you are on eBay and you're trying to do something, we try to understand what you're trying to do and try to target to help users achieve their goals faster. Other use cases is, when users come to eBay, there is a whole bunch of campaigns which are run on eBay, and we try to optimize what campaign to show to whom based on their current actions and their past behaviors. So just kind of in this use case, the requirements from real-time analytics perspective, we need to have a system which has a very low latency, I mean sub-second typically, because users are going between pages and we are trying to make a decision when the user goes to next page to target or to do a different campaign delivery to the user. The events which are coming across multiple devices and web browsers tend to be in millions per second. And final thing, data accuracy. So this actually is from our observations, has been a very challenging area. So our data sources are lossy. They are all over internet. Internet has a certain rate of loss that we see when the signals come to us. Now, it's very important that we build a system which can compensate for these losses. Okay. I'll go on to the next use case, which is in the monitoring space. Monitoring, we essentially look at our data centers, our hardware, our applications, our network switches, and across the board, we use a centralized system to monitor all of these infrastructure. So inputs here are essentially heartbeats, SNMP traps, logs from all of these devices. And the problem statement that we have is essentially collect, aggregate to give high-level views on how a service is performing, how a data center is performing, and so on. And as secondary, this primary requirement along with this is to look at things which are out of order, and this might be a service which is very hot, or dependency which is breaking apart, and we need to do corrective actions both through automated systems as well as human action. So these are more in correlation and alerting space. The requirements for a system like this, again, it's the scalability requirements are huge. We deal with tens of millions of events per second. Availability, this is a system which monitors the rest of the site, so it has to be 99.99 if not 100% available. Thing to call out, a system like this in a real-time use case has to be up no matter what is going on, whether there are software patches being applied to the system, whether there are new software being deployed to the system. We cannot take downtime because the rest of the data centers and machines and so on are not taking their downtime. Flexibility, a system like this requires users to have their custom rules. They would go ahead and, depending on each service, they would come up with their custom definitions of what is an anomaly. It needs joins with other data sources, so you might have change happening at a downstream service level, which might impact your service. So joining data across those services is extremely important. Third use case, we are still setting up the background for the problem statement that we are looking at. Again, traffic security is a use case where we try to understand users who are trying to do DOS attacks at eBay, or bots who are trying to utilize our resources and we want to protect against them. Requirements here are similar in nature. Tens of millions of events per second. We need very low latency reactions to these events. And the data accuracy, again, the thing to call out here is in all of these use cases, the sources themselves are lossy in nature. So our system has to compensate and actually using statistical methods have be able to deal with 99% data accuracy. So product requirements end-to-end, we're looking at high scale.
I have a quick question.
Sure.
The questioner asks, do these three business cases require fundamentally a different design, or did you have to, or does a common design accommodate these three different use cases?
So we are going to present a common design across all 3 use cases. While the design is same, the deployment in each one of the use cases have some variances, of course. But the core architecture and the core design is same across all 3.
Okay, so I guess to follow up, and the individual can jump in as well. I've unmuted you. If there are sort of system design issues that would be different in cases, from use case to use case, it'll be great if you can point that out, just so that people have an understanding as to how system design changes depending on the use case.
Sure. So let me go on to summarize the product requirements, and we will actually, as we go through the presentation, our presentation is more oriented on the common infrastructure behind this, but we can have a one-on-one conversation with the individual to talk about how we deployed it differently in each one of these use cases. So availability, as I mentioned, these systems are very critical to eBay. Monitoring system cannot be down, because if it's down, you don't know what else is down. So our targeting system, if it's down, we are losing the capability to target users correctly. So they have to have close to 100% availability, all of these systems. Flexibility. So what we have seen is there's a lot of need for user-driven rules, and they can be fairly complex. I gave an example in the monitoring system. You could have joins of multiple streams, in this case the CPU stream and the transaction per second, TPS stream and the error stream happening. These are actually ad hoc rules. We don't build streams for these rules. Users deploy their rules on existing streams. So business need-wise, they want to run a very flexible set of rules on these streams and get signals out of it. Finally, data accuracy. We look at dealing with missing data is extremely important. Extrapolating data, and actually inherently in our architecture, we have to deal with a system which is from data accuracy perspective 99.9. However, availability has to be 4 nines or even 5 nines. We cannot ever bring down the system for anything.
One more question. Regarding the user-driven rules, can you explain a bit as to who the user is and who writes the rules? Are those two the same, or are they different?
They are the same. So what we want is every service owner to be able to author rules in the system for their service. They're typically the author, they life cycle the rule, and they maintain the rule. So from an infrastructure provider, we do not play a part in writing or deploying the rules. However, from infrastructure perspective, it's extremely important that we protect the system, so that you could easily write a rule which could impact the system. So there are sandboxing mechanics, and there are throttling mechanics on these rules. But apart from that, our business need is users should be able to write their own rules.
Okay, I guess a quick follow-on, Bhaven. The assumption, therefore, is that the service owners are internal eBay users who provide services to your customers, I'd imagine, correct?
That is correct. So an example of a service owner might be an application service provider, let's say checkout service, or it could be an infrastructure service provider like the load balancer infrastructure. So there's a team which is responsible for that, and that they own that service, and they would be writing rules on the system to identify anomalies in the system.
Okay, and one more question that's coming on a different track. What is the system configuration for real-time analytics, low-power cores with high-end I/O using commodity server hardware? Can you just give a flavor of the kinds of hardware that is deployed that is optimal for this kind of workload?
Sure. So actually, we will go into some amount of detail there. But the short answer here is that we want to be cloud friendly. So we run our infrastructure on cloud VMs. They tend to be low power cores. Actually, our CPU needs are not that high. However, we like to have bigger memory profiles and more network capacity in the systems. but we will actually deep dive more into that. So at this point, I'll hand the presentation over to Sharad Murthy, who is the principal architect for this infrastructure. He will take you through a journey of our architectural considerations when we were building this system and what we observed, and end it with a demo.
Good afternoon, everyone. This is Sharad Murthy here. So what Bhaven touched upon is a varied set of use cases, and what comes out of that is there are certain systemic qualities that we are looking for in the design. They come as requirements from the business use cases that we tend to solve here. Latency was the key driver for a lot of the decisions that we made in the architecture. We want to react in sub-second most of the time, 1 to 2 seconds, many other times. That means that the infrastructure has to have extremely low latency as we process events in the infrastructure. Availability has to be 4 nines. We wanted to scale to hundreds of thousands of events per second, but in fact it's a lot higher. And the accuracy, that means the data loss in the system has to be pretty low, right? All these requirements are pulling against each other. So to consider a system like this, we had to look deep in terms of how we were to solve and meet these requirements. If the core concept for us was not to consider store and process model. That would never work in this environment. So what we started off with a concept where we would completely absorb the stream of events coming from applications right into in-memory processing cloud. We essentially create a DAG of processing elements and stream the events through them. And as we do that, we enrich and aggregate the data in these processing elements. As part of the enrichment and aggregation, there are times when we have to look up data sources. Some of them are static. We actually host these data sources right in the processing element itself. In other cases, we have to look outside, so we do the joins. As the stream egresses, one of the requirements that we had was most of our consumers would come and go as they please. We had to have a pub/sub model, so they could subscribe to certain data feeds. The signals that we produce essentially can be mutated, are derived from mutations of the original stream. We apply filtering and then we serve them. One of the key concepts that we were looking for is how flexibly the user could write rules in the system so that they could get what they want out of the system. We looked at the various solves. Seems like SQL seemed like a common theme across all the users. People are familiar with it. So one of the things that we're looking for is people to write these rules and for us to provide the tools for them to make that happen. And CP engine seemed like the right solve for this kind of a problem set. So we, in our system, have picked, or rather we use CP engines very heavily in most of the processing elements that we have written. And whenever we can't use CP engines, we augment that with custom processors. So
Sharad, quick interrupt.
Yeah.
If you don't mind, 2 questions have come in, and you can decide when you think you want to address them, but I'll just share them with you. The first question is data security not a concern in this system? If so, how does that impact latency? And the second question is, how is this approach that you've outlined in this slide different than, say, a Spark framework from Berkeley, of in-memory computational large-scale data processing? So, if you can address those, or you're already addressing them at some point, then that's cool. Thanks.
So, first of all, right, so the Spark comparison, I'll keep it to the end. I have a slide on that, but I think as the story evolves, you will know some of the differences will come out. But in terms of data security, for user behavior analytics, we make it a point that there's no PI data flowing into the system, right? The second thing is our data consumers, when they get the data, we push the data to them. So there is a way in which we validate who's authorized to get what data, and we only push that. So that kind of enforces security in the system. Any other questions?
Yeah. Thanks, folks.
Okay.
If anybody asks a question and want to follow up, send me a ping, and I'll connect you with Sharad and Bhaven directly. Thanks.
So let me take you to our deployment architecture. So essentially, what we do is the processing elements that I showed you in the previous slide, they constitute a CEP cell. This is a Java application, and I'm showing you a very small pipeline that a particular cell hosts. And this is very typical of what we do. We bring in events, we ingest them, we process them, and we've written some custom processors that encapsulate a CEP engine and feed SQL to it. And whatever aggregates or mutations or filtering that we do here, the output of that is fed to some channel or some processor, and then it gets served out. So the way we organize these CEP cells is we cluster them in a logical ring. The rings can span across multiple data centers. So in our case, since we operate in a cloud environment, essentially we cannot control where an application is going to run. It will run in some data centers somewhere. And what we want here is a mechanism for these CEP cell instances to come up and advertise themselves, so the producing clusters can discover them. So in this particular architecture, we don't have any hardware load balancers or anything like that. The producers talk directly to the consumers. They discover the discovery process, and we use Zookeeper for that. So once the consumers are discovered by the producers talk directly to the consumers, and we can have as many rings as we want, and we manage this throughout the system. Now, one of the things that we do is the system can, the pipeline that you see here shows you a SQL, and we kind of provision these at runtime. So there's no concept of bringing the system down. In our case, the system has to operate continuously. So what we do is we can update rules written in SQL on the fly, and that is done through a MongoDB. We use that as a config database, and there is a config management system that supplies the configuration online. So once SQL comes in, it basically gets compiled at runtime. So these rings are basically self-balanced rings, and this is core to our scaling and availability architecture. So I'll talk more about that in some of the next slides. So the building blocks for a framework that we have built are essentially channels and processors, right? Our events are tuples of information. We only support one type of event, which is a map of tuples. And in our case, these events are mutable. So as they flow through the DAG, we can enrich these events, we can remove things. They just had to be mutable in our case. So the other thing that the framework provides is a way to stitch the pipeline. Right? Pipelining is supported in a form which is very different, where we don't stitch the pipeline at build time. We stitched at runtime, and you could change it. We also support batching, very similar to what I think Spark supports. So the user has the option to pick either of the models. One of the key considerations here that we have in our pipeline is we can control the flow of events through the DAG. As the system is up, there are certain semantics that we use to make sure that we can programmatically control through SQL how these events flow through the DAG. So let me talk about what a cell is. I introduced the concept of a cell. Cell is nothing but a Java application hosting a Spring container, and the Spring container is where the Spring beans, which form the stages, are hosted. So one of the key considerations for us in picking Spring was that we could really stitch the pipeline at runtime and then modify it at runtime too. So if you look at Spring, Spring does not allow you to make any changes to the beans or the container once the container is created. It's pretty much immutable.
Sharad?
Yeah.
Question has come in, and the question is, what constitutes an event in your system? And number two, what is the granularity of such an event?
So an event in our world is a set of tuples, right? And in terms of granularity, we can have nested events too, right? It's basically a data structure which is a set of tuples, key value pairs. That's what we stream, and all we need is we can basically ingest anything that conforms to this, and we declare that to the engine, just like you declare a database schema to a database.
I see. So therefore, your users could be defining these tuples, basically.
Absolutely. It's completely, we never have to, this pipeline or the infrastructure never has to roll code just because the event changed, right? It could come with any piece of information, and as long as you don't run queries on the data set, you're fine. When you have to run queries on the data set, you have to declare the schema to the engine. That is how our system works.
So an example of such an event could be, just to sort of make it concrete in people's minds in the context of your application, would be what?
So imagine a click stream, right? So a click stream comes with, say, a page ID, the page that the user clicked on, some other things that are relevant to the page, some claims, maybe explicit or implicit, that would have been collected by the application. And these will flow into the pipeline, right, where it is ingested and analyzed. So the other use case that Bhaven was talking about was monitoring. In the monitoring case, it could be CPU, memory, application ID, pool name, so on and so forth. So the same pipeline, in theory, can be used for analyzing both these streams. And we do this all the time, right? So what Spring provides us is a syntax. So this is a Spring IOC model. We wire the applications using the syntax. Because we have this XML form, we are able to make changes to the running application. The whole topology can be changed just by doing this. And we have tools that enable us to do that. So if you look at our application stack, Spring is our core. We are a Spring-based stream processing framework. Spring gives us a container, and then we built a stream processing framework that essentially people can use to build their own custom processors, connectors, and channels. CP engine, we have picked Esper, but we have a loose coupling to Esper. If we find something better, it is very easy to replace it. One of the things for us is that in eBay, everything runs on our cloud infrastructure. So we've gone about building tools to basically enable applications to be provisioned and deployed in the cloud. There are monitoring tools that are available. Most of the applications have a REST interface to monitoring, and every stage you can watch how the events are flowing in. All the counters are exposed. And you can even view the event as you're streaming through stages through a monitoring REST interface. We also support a Dockerized model of the application. We support tools so that Docker files are generated, and you could deploy the applications in Dockers. In the eBay world, we don't use Dockers. We have a custom cloud, and we support that internally. But we have instances running on EC2 in Dockers at this point. So if you look at the core concepts of availability and scalability, the way we achieve that is through this ring architecture. So one of the core considerations for us is that the applications have to be self-healing, right? So what we do is generally when you deploy this in this ring, the producers schedule events into the ring. We use a push model. We don't use a pull model like a lot of the exactly once semantics-driven solutions, right? The reason why we do this will be explained in the next 1 or 2 slides. The key here is if a cell goes down in the ring, the producers discover that, and it automatically rebalances traffic. If you throw a new cell into the ring, it auto-joins the cluster. There's no provisioning needed in the system. The producers, there's a protocol that allows us to discover new cells that are joining the cluster, and also when a cell leaves the cluster, it basically is detected by the producer. The other thing that happens all the time is we have slowness in the network. So when you have slowness in the network, you'll typically find that the queues build up on the producer side. And this typically happens when we go across data centers, right? So one of the solves we have for that is that we can use Kafka as an off-heap queue in such circumstances and then replay those events. The CP cells sometimes have state that we want to preserve, right? When the traffic gets rebalanced, the state has to be restored. So for that, we have a state store where we keep all the state in these applications and then we restore them. The other thing that we want is graceful shutdown. So when an application, say, is going through a software rollout, at that point, we can orchestrate the shutdown sequence. So the framework provides that capability. It goes, shuts down from ingress to egress, and traffic gets rerouted at that point, and any aggregates that are accumulated are flushed out. The other thing that we need is dynamic partitioning. So what I mean by that is this cluster gets sharded. Most of the aggregates that we compute in memory require us to have stream affinity. There are different schedulers that are supported by networking or the messaging stack, and we can pass hints down to the messaging tier to create stream affinity. And the way this works is that a particular tuple in the event is used as affinity key, and based on that, a consistent hashing algorithm runs, which determines where to schedule the event. The clusters are completely elastic. They can go up and down. What we don't have at this point is a resource manager, but in our cloud, we have flex APIs that we use to flex up and down as we desire. But once we go with Docker containers, we might probably integrate with something like Mesos. The first, one of the earlier slides, I was talking about how we mutate, filter, and send to our subscribers, who are our consumers, essentially. There, what we need is complete control over routing the streams. So what we have built into the infrastructure is dynamic flow routing. We pick routes, and we can write these rules in SQL in terms of where they will be forwarded. The other thing that we need is dynamic topology changes. And this is one key aspect that we've emphasized a lot in our decisioning here. When the cells are initially populated, right? We never have anything at build time, as I said. We could wire it in one way and all of a sudden realize that, oh, gee, we need to add more stages within a particular application boundary. So in that case, we change the topology. We roll that into the cluster as the events are flowing in. So in terms of
Sharad, 2 questions.
Yeah.
Is pipelining only done intra-cell, or is it also done between cells within a ring?
It is done between cells. It actually goes over the wire.
Okay.
So I was going to talk about that. Is there another question?
Yes, there is. The producer sends events to specific cells or all cells. What is the concept of load balancing here? Is it the number of events per cell?
No, actually, very good question. The load balancing aspect, there's 2 aspects to it, right? It depends on the kind of scheduler you have deployed. So we support 2 types of scheduling. Either we can go balance the load across the ring, where we just do weighted round robin, and in which case every other event is sent to the next node, right, next cell. However, if there is stream affinity, then the stream essentially is pinned to a particular node. So if, let's say, I had an event stream where one of the fields was X and X had a value of 5. So as long as if I pick X as my stream affinity key, then if the value of 5 was seen, it always lands on the same node. The whole event lands there. So our model, basically that can be controlled programmatically in SQL in our world. Any other questions?
No, thanks. Thanks.
Okay. So in terms of messaging, we support both push as well as pull models, right? What we've gone with is mostly push, but we have a hybrid model that is what serves this pipeline. Push model, the advantage you get is there's no middleman, no broker. It goes directly. So for low latency use cases like what we are dealing with, push model has turned out to be very good for us. Unfortunately, it has this drawback of having, let me just change this one. It has a drawback of at most once delivering semantics. And the problem is really with slow consumers, right? When, since most of these applications are built with Java, there is a GC pause or there's a network issue, the queues build up in the producer, and we can't store them anywhere. So the disadvantage is that we might drop events. However, if we went with the pull model, go ahead. So the pull model is what you would achieve with a Kafka-like solution, where you would write to a persistent queue and then you pull the event at leisure. Now, you ultimately have to have capacity in both models because queues can build up in persistent queues and then you have to drain them, right? But what we are saying here is that we can. It's hard for us to say that we can do exactly one semantics. We definitely do at least once semantics with a pull model, but we can achieve exactly once with the pull model. The core concept here is that if I go with the pull model, you have complete control over how you consume this data in the cell. However, the cell cannot have any forks within the cell. So that is one limitation that we have. However, if you went with the push model, you can do forks and joins, whatever you want. There could be an issue of loss. So what we do is we pick the hybrid model. In a hybrid model, the consumer, using pipeline flow control, can signal back to the producer. It is more like what the reactive streams specification is. I mean, we thought about this 3 years or 4 years back, so this is kind of a older concept than what reactive streams has. In this concept, the consumer can push back producer and say, don't send me anymore, right? The producer at that point takes that and rebalances the traffic. Or the producer can stick the events into a broker, into a persistent queue, and then we have a replayer app that replays that. So with this model, we are able to achieve like very low losses in a pipeline. The one caveat of this is that you will have out of order events sometimes, but this works very well in scenarios where you have temporary network glitches or applications being swamped because of GC issues or whatever other issues they might suffer.
Sorry, folks, our IT guys have.
That's okay. I think we all know what updates are.
So in our case, we have this concept of false resume in pipeline flow control, and this actually flows from stage to stage in the cell and travels all the way over the wire into a producing cluster. So this allows us to rebalance traffic whenever we want. And also, as part of software upgrade, this is what we do. We typically take a application out gracefully by signaling this way and then upgrading the software. So now
there's a question here.
Yeah.
And the question is, it seems that cells are basic units of computation, and cells can be put in for dynamically stitching the pipeline. If that is true, how do you ensure that pipeline latency stays within the required latency budgets?
So, see, it's like this, right? When cells come and go, they basically signal to the producer to rebalance traffic. to take traffic out of that particular cell. So at that point, traffic is rerouted somewhere else. So we never pause. Yes, there will be hiccups. Once in a while, you will see your latencies will shoot up. But on the average, we measure very low latencies over a 4-stage pipeline. We see like 100 milliseconds across data centers. And most of our data centers are designed in such a way that networking between them gives us barely 17 millisecond latency. So we are able to do very high rates at very low latencies because of this architecture.
Thank you.
So now I'm going to talk about the flexibility aspect of the system. One of the things with Esper is Esper programming model is super complex. I think if you just program to the API and use SQL, it is very hard to do it. In our case, what we've done is we've taken Esper and we have built tooling and infrastructure around it, which has made the use of Esper super easy. We use this for doing both rolling and tumbling analysis over rolling and tumbling windows of time. Most of the security use cases actually rely on rolling window of time, whereas a lot of the user behavior analytics use tumbling windows of time, right? We can do filtering, joins, multi-dimensional metric aggregation through grouping and ordering, event mutation, correlation. All this is done using SQL in our world. So for us, the key here is the data model is very simple. We don't support complex types. We actually don't even recommend people using complex types. What we suggest to people is to use tuples, and the value of the tuple typically is one of the primitives that the language supports. If you go with a complex type, you'll end up rolling code all the time. All the tiers will depend on upgrade. So this is why we kind of stay with this, but you can do nested maps here. You can go many levels deep in terms of how you specify this map. The key here is that you have to define this to the engine. You have to declare upfront before you make a query on the stream using any of these fields. So we provide you the infrastructure and the tooling to do that. Whenever you submit queries, before you do that, you'll have to define the event type to the engine. So I'll take you through some EPLs and show you what we've done with SQL, right? So the syntax that you see here is the Esper syntax, and what I'm trying to do here is I'm trying to monitor a particular dimension called D1, which is a field in the event, and I'm trying to count the number of occurrences of this D1 over a 10-second window, and I use filtering by only reading events where one of the dimensions D5 has a value of 1, and then I emit an output when the count for D1 goes beyond 8. And I rate limited the output by using a rate limit clause here. So if you look at the picture at the bottom, what you see is a snapshot of a pipeline where a CEP has two sinks. I use OMC and OKC as acronyms. OMC is outbound message channel and OKC is outbound Kafka channel. So what I want to achieve here is I want to tell the SQL engine to evaluate the select statement, and then the results of the evaluation, I want it to send that to a particular state in the pipeline. SQL by itself cannot do this, right? So what we have done is we have come up with an annotation plugin framework where people can build custom annotations. We actually support some of these annotations as part of the framework. So with an output to annotation, I'm able to direct the evaluation results to a particular sink of the CEP engine, right? At the same time, when I want to send it out across a cluster to another cluster, I can, since I have PubSub messaging, I can publish on a certain topic. And that way, the evaluation results are taken and then they're shipped across to the right cluster. And I can do this whether it is the custom cluster messaging that we have written or it's Kafka. It works the same way. I can even do it with the REST. If I were to hook in a REST channel here, I will be able to send to a specific REST endpoint just by doing this. Now I'm going to take you through an example that shows how we filter, mutate, and rotate, and I'm going to introduce a new term here, right? So this particular EPL that you see is pretty simple. It picks up D1, D2, D3, and D4 from the stream. And there are a lot more dimensions in the stream, but it just picks up these four. And it filters with the in clause, and then it does some more checks. Once the stream route stream is populated, I go and do a select from it. At this point, the first two annotations you saw in the previous slide, where basically I control the flow of events. But now, the interesting thing is I have two clusters downstream, and what I want to do is I want to ping the stream to a specific node in the downstream clusters. So I pick one of the fields in the stream. In this case, it's D2, and I tell the underlying messaging layer to take this and create a stream affinity. And all this is done in SQL. So I can do this for as many statements as you want. One more. How much time do we have? Okay, yeah, almost done. So one more complex thing that I want to introduce after this is that, so let's say that I'm trying to compute multi-dimensional metric. So as I compute the multi-dimensional metric, one of the things that I can do in this particular case is event comes in, I make the computation. Now the computation is grouped, the aggregate is grouped by D1 and D2 as dimensions, but the sharding for incoming events is, let's say, on D3, which is not part of this grouping. So now the problem is you have the same metrics landing on multiple nodes or multiple cells. You need to aggregate this one more time across the cluster. For this, you can create a new dimension. So the dimension, create dimension annotation creates a new dimension, and you can give it a span as to how many columns or how many fields this particular dimension is spans, and then use that as an affinity key. So now you can loop back events. So there are many such annotations that we have produced. I'm just taking you through some of the annotations that we have in the system. The other thing that we have built now is for a lot of the computation that we do, we are very interested in always finding out the top end of something, or we want a distinct count of something else, or calculate percentiles, right? So these are very complex and heavy computations. They require, which are both heavy in terms of time and space. And it gets worse as the cardinality of the dimension increases. So one of the things that we are moving towards and have an initial implementation of is using approximate algorithms. So what we want to do here is we want to trade off accuracy for performance. So these are available to us, or we've written these as user-defined functions, which we call in our SQL statements. This cuts down the overhead enormously. So this is how we are moving. A lot of the algorithms are going to be implemented this way moving forward. So this kind of shows you how we deploy SQL at runtime. So the key difference here between us and a lot of the other solves, or rather if we had just used the Esper engine as is, we would have to roll Java code every time we change EPL. So instead of that, what we do is we submit SQL to the cell itself. So SQL lands at the cell, and it gets compiled to Java code and further compiled to Java bytecode, all at runtime. And what we do essentially is we create a new engine instance, we compile it, and then we swap the engine. So there's never a drop in performance or any drop in events. This happens as events are streaming in, and you can change the SQL statements as many times as you want, and the entire cluster gets updated all at the same time. So what I want to do now is to walk you through the pipeline that we've built. This is what Bhaven was talking about, right? The use cases that we've built essentially are served by this pipeline. And what I'm showing you here is the pipeline that we use for user behavior analytics. It is a 4-stage pipeline. Each stage is its own application, and they're all deployed in our cloud. We ingest events from 100,000 nodes into a collection tier. And this is where our bot detection algorithms run, and we detect bots and filter the events that are bot associated. And then as we stream this into our next tier, we are able to enrich the event. And web analytics actually requires us to sessionize the events. And so what we've done is built a sessionization tier where we can sessionize events, and we have a session DB where we store the session state. And we are able to restore this state whenever there is a movement of the sessions. Now, the key thing here is that there is a GeoDB that is hosted right in the application tier. So we use a high-cut-like algorithm to walk GeoDB for doing spatial searches. So all this is injected right as the events are flowing in. And finally, we come to a distribution tier from where we can distribute the events to our consumers. Now, the scheduling between collector tier, and the enrichment tier is using consistent hashing rings. However, the scheduling from the enrichment tier down to the distribution tier is using weighted round robin. So we tend to change this as the need rises. And from the distribution tier, our consumers sometimes need stream affinity. So we are able to schedule them as and when the consumers require us to schedule in a particular way. Now, metrics calculator is our last stage. This is where we compute aggregates, right? Multi-dimensional aggregates. And this is where we are able to do alerting. The signals produced by the metrics calculator can either be visualized or it can be served to other applications that can act on it. This entire pipeline, the latency is only 100 milliseconds from the time the event enters in to the time the event enters out, leaves the distributor and reaches the consumer. So on the average, we've seen losses, steady state losses to the tune of about 0.01%. And the system's been running for more than a year and we've never brought it down so far. We've done several code rollouts, but the pipeline has never been down, right? What I want to do next is to talk about the key takeaways. So the key things that we have built are the concept of creating pipelines declaratively. This allows us to change the topology at runtime. We've introduced the concept of SQL-driven processing with hot deployment of SQL. We don't have to write Java code or code in some language to submit SQL. We can do this as the system is running. We provide an extension, a framework for extending SQL, the kind of annotation that you saw. We're able to dynamically partition and control flow through the pipeline. And this completely operates in the cloud. We are able to, in fact, most of our customers also operate in the cloud. Going forward, we might want to do this on a Yarn infrastructure, but as of now, what I'm going to do is take you through a demo.
Sharad, I will, so folks, this is Bhaven, I will go over the demo. Before we go over the demo, just some key takeaways. You know, in any architecture, there are gives and takes. In our case, availability was not negotiable, scale was not negotiable, flexibility was not negotiable. However, in our case, you know, our use cases from sources were inherently lossy, so some amount of data loss was acceptable. Actually, 0.01% where sources themselves are losing 2 to 3% of data. It's perfectly okay in our system. So as you saw through our architecture, we always made choices which would allow us to keep the availability high, the scalability high, and so on. So what we will do next is give you a quick demo on an application. It's a simple application on top of the string. But the key thing to take out is this application was written without any downtime by an end user, without us getting involved in the system. So that is very important for us. As we build the infrastructure, we want people to build newer applications on top of this infrastructure. So let me just go on. So here, what we are showing is a real-time view of all checkouts as they are happening right now at eBay. So what you see is the red dots over Europe and United States and some other parts of the world. And these are happening within the last 1 minute, actually. Okay. So the team which built this is actually one of our monitoring team which wants to look at a global view of how things are happening on the site. They actually built this on top of the pipeline as a self-service app using the SQL paradigm which Sharad talked about. So getting back to our presentation, we have come a long way in this journey. We have several mission-critical applications running on these streams. We are looking at, actually, we are open sourcing this infrastructure. We actually have a set of Dockerized instances running in EC2 right now, and by end of Q1, by end of March, this will be made publicly available. It will be under the name of Pulsar. We made a lot of progress, but there's still a lot of interesting problems to solve out here. We look at the long time windows. So today we do rolling window aggregations over up to 30 minutes time window, but there are use cases which require days and hours worth of rolling window aggregations. So longer term state storage, reliable state storage is something that we are looking at. Scaling it for specifically on a storage end, we are looking at stores which can go up to 1 million inserts and upserts per second. Joins with other data sources. While we do support small joins, like you saw in the GeoDB and device classification, large joins today are require some work from the end user. So we want to formalize the model of joins with graph and RDBMS tables. So at this point, we'll go over, somebody asked earlier, how does this compare to other offerings in the market? By this time, you kind of would have gotten our thinking, availability, scalability, flexibility, trumps, everything else in our model. That's the business need, actually. We run systems which are not allowed to go down ever, actually. So a lot of our decisions were based on that. So if you look at how we compare against Storm Trident and Spark Streaming, declarative changes, anywhere where you essentially want to change the topology, add a new rule to the system, put a new software patch to the system, and so on. At least from best of our understanding, these cannot be done looking at the architecture of Storm and Spark, which kind of, the corollaries to that, pipeline stitching or topology changes or SQL support on the system and so on. The aspect where actually we made a compromise on our end was, should we look at exactly once delivery semantics as core of our design principle? As I mentioned earlier in the business use cases, that was not necessarily needed in our system. We needed at most once semantics with 99.9% guarantees of data delivery, but that was good enough for our use cases from a business perspective. So that was an architectural decision that we made in favor of flexibility, in favor of scale, in favor of systems which are always available. So with this, we are open for any questions.
So I guess thanks, Bhaven and Sharad. While people, I already have a few questions here. Folks, send in your questions. We're going to lose a few people. I think we've already lost a few. But for those that need to run immediately, thank you so much for attending. Please do fill out the seminar survey. Send me any questions. If Bhaven's coordinates and Sharad's coordinates are not here, feel free to send me email and I'll connect you with them directly. And then, our next webinar is going to be on Feb 27th, and I'll give you more details about that. You can also see that on the website. So I guess with that, let's, Bhaven and Sharad, I'm assuming you can still stay on for a few minutes, correct?
Yes.
Okay. So then let's start with questions. There are quite a few that have come in. I guess the first question is, Is the ring architecture selected for scalability purposes? That's question one. Question two, how do you balance ring depth with low latency requirements?
So yes, the ring architecture is for scalability consideration and also for it to go across multiple data centers. We want the ring to be deployed in such a way that when it goes across data centers, if there's data center failure, we can rebalance the ring and move the entire traffic out of one data center to another data center. So that is the advantage you get. So in terms of latency, actually latency is determined by the producer talking to the consumer. That is what determines the latency, right? I mean, the ring by itself doesn't really play into that part. Latency is determined by how soon or how quickly can you get the event from the producer to the consumer, and how quickly can the consumer process the event. The latency is typically generated by the consumer making call-outs to some services, which might take its own long time to respond. So one of the things that we do in this pipeline is we try to minimize any call-out, right? We try to do everything in memory. For example, you saw the decision that we made in terms of the GeoDB, right? There is a service within eBay we could have easily called, but we decided not to do that. The GeoDB feeds come on a monthly basis, and we carve out a nice DB that fits right in memory in Java heap, which is about 100 megabytes in size, and we have special algorithms that can go run that very, very quickly. Within 100 microseconds, we are able to do a lookup. Same with device classifier. We have made the decision to host it right within a cell so that we don't go outside. So as long as you minimize external lookups, you will guarantee that latency is always going to be low.
Yeah, I think to add to Sharad's point, the core consideration for ring was actually availability. We run on clouds where machines are expected to fail once in a while. Actually, we had a strong requirement that when data centers fail, we should still be able, our system should still be up. So having this the stream run across multiple data centers with automatic failovers was a key requirement. So ring gives us that. It allows us to balance traffic, so it has a scalability aspect to it. It is balanced across, the traffic is balanced through consistent hashing techniques with user-driven keys if needed, actually.
Now, I have to admit here that there will be occasions when you might get a storm. This happens mostly with bots, right? A particular bot comes and hits you at a very high rate, you could overwhelm a shard, right? What you're doing is you overwhelm a partition. It's always going to land in the same node. So for that, what we've done is built rate limiters. So the cells, actually I didn't show this, cells have rate limiters built in. You can inject that in, and it will just figure out the traffic, and it uses a frequency estimation algorithm to figure out who is the abuser, and only selected abusers are, the events associated with the selected abusers are dropped at that point.
I see. Folks, those that need to follow up, please, there's a bunch of questions, so Sharad and Bhaven, I'll just roll to the next question. What are the typical causes of data loss? Is this mostly due to pipeline being down, or can underlying algorithm also cause loss in data?
Absolutely. If you submit bad SQL, you will stop, the engine will reject. It will not be able to evaluate any of the expressions. Typically what we do is when you get into that kind of a scenario, we have a mechanism where you can listen for advice. The engine will advise you saying it couldn't process a particular event, and we take that and we put it back into Kafka and replay it. So you could go in circles here, and the replay always is throttled, right? It doesn't come right back. We throttle that. So that is one scenario where you could produce a problem. So most of the times we find that it is the network that causes this, especially when you go across data centers, right? In a cloud environment, you cannot predict which path you're going to take. And it is on a 10 gig link. 10 gig is signal quality is not that good. You always tend to have a lot of TCP retransmits. That causes queue build-up, slowness, or if the Java application itself starts misbehaving, because there's too much GC activity, right? Typically, if you look at all these pipelines, we have designed these apps in such a way that there's hardly any temporary objects being created, right? And we make sure that most of the GC pauses are within 5 or 6 milliseconds. However, there are times when, it's not just your code that's sitting there, or you might not have anticipated something with GC shoots up. In that case, you will see backpressure building up. So that can create loss. But with the kind of design we have, we are able to minimize those losses considerably.
So just to give you our experience, over a year, we have had 99.99 availability of the pipelines, various pipelines that we talked about. Data losses happen when machines disappear in the system. So, you'll have a temporary blip when one of the cells die and the other cells take over. It can happen because of network back pressures and so on. But in general, we have essentially worked towards our requirement, which was 99.99 for this system. So.
Okay. Let me run through a few more questions. How distributed is your data center? You showed, I think, in the demo, Germany and Asia, etc. But were there any particular architectural implications depending on how geographically distributed your data centers were?
So we have multiple data centers. I'm not allowed to say where and how many. But eBay, like any big internet provider site does have multiple data centers. All of our software is built with the concept of disaster recovery, as in a data center can go down and our software still has to run. So we have to, it is very important for us when we were building, only way we could have gotten 99.99 was to have the disaster recovery concepts built across data centers.
Okay. Let's see, cycling through the other questions. Any statement you can make about what's the backplane I/O being used between data centers?
Yeah, it's all 10 gig. We have a dedicated link between data centers. It's a T1 link, and the kind of architecture we have at the network layer, it kind of guarantees that between data centers, the latency is about between 13 and 17 milliseconds, a max of 17 milliseconds.
Okay. Next question, any processing redundancy to handle errors and delay?
So I want to make another point here, right? The thing about going with the ring architecture was to look at a typical HA solution, you always have a backup. For every processing element, we would have to have a backup. With the ring architecture, what we are doing is we are over-provisioning a little bit. So if there is any loss somewhere, the data is, the aggregates are moved to another node, right? They automatically go. But the disadvantage is that sometimes if you don't have a backing store to restore the state, the aggregates start from scratch, right? The counts are all going to be starting from 0 again. Other than that, there's no other magic here, right? The ring is what does that for us. It is cheap. You operate active all the time across data centers. There's no active passive. So the cost is a lot lower with this architecture than having to run this pipeline twice. And then when you look at data, you don't know which one is correct, right, at that point. So here it's like everything is balanced.
Okay. Let's see. I think there are a few more questions, but we may be running out of time here depending on how long you guys are able to stay. I guess it's interesting that you guys chose SQL as a query language. And obviously you showed a bunch of different examples where that works out perfectly. Are there any interesting use cases where you might actually need plug-in code as opposed to SQL?
Yeah, there are a lot of use cases, right? So think about it this way. Let's say that one of the use cases that is run on this using this technology is MLR, machine learned ranking, right? The search guys use this all the time. I mean, that you cannot do in SQL. They are like complex algorithms that are implemented. That has to be implemented in Java or Scala. So they write custom processes at that point. I mean, it's impossible to do it in SQL. So that's why I said we'll use SQL for the most part. We'll augment it with UDF. Sometimes even UDF doesn't make sense. So in that case, right, you introduce a stage which is doing this complex algorithms outside of SQL.
So just to add to Sharad's point, when you do write Java code, you can write any logic in Java code, and people do write it. But at that point, we don't have hot deployment capability. That is one of our future to-do works, actually. So in these cases, the cluster has to go down for some time.
Yeah.
So it is something which, at least internally, we don't prefer because of the obvious issue that it has an availability impact.
I see. And so if you do support, custom Java or Scala code being ingested for query purposes, I'd imagine then obviously your own platform can no longer make any SLA guarantees, right?
That is correct. So a typical model that we look at in these sort of use cases is we have this concept of a mother stream where data is flowing through and where we have strict controls with SLAs. And then we create child streams. So in Sharad's previous use case where somebody wanted to run machine learn ranking, that's a very dangerous thing to run on the mother stream because you can easily create algorithms which would be very expensive. So what we will do is we'll create child streams, pump data into these subsystems, and let them iterate over their availability profile.
So imagine this pipeline, right, that we showed you is this never deploys any algorithms like this. The consumers of the data that is coming out of the pipeline. Pipeline enriches, it creates metrics, it observes things, it notifies, and then it creates all these substreams. The way the system works is that people can, or consumer applications can come and join at the end of the graph as they please. There is no concept of, hey, just because I wanted a new algorithm, I have to roll new code again and redeploy the whole pipeline. It's a pub-sub model. They just come, they subscribe to a specific substream, and then they start getting that. And when they go off, they cause no perturbations in the pipeline.
Substream creation in our case is self-service. Yeah. So we, of course, we have rate limiting, as in the substream cannot be the whole mother stream kind of a situation. But apart from that, people can come up with their filters, create the substream, and do whatever they want in their sandbox.
Okay. Folks, I know you guys need to run as well. I think Bhaven and Sharad, you guys indicated that this sort of the Pulsar platform will be open sourced. Obviously, there are quite a few folks, both in universities as well as others in our network, who might be interested, when that happens. So if you can just make a note to send me an email when that happens, maybe with a GitHub URL, I'll be sure to pass it on. Of course, you guys, I think you mentioned that the project name is Pulsar, so folks can also search for that. If there are no further questions, I guess one last question, since there are a few faculty, what kinds of interesting algorithms do you see as being open questions for which maybe folks currently pursuing PhDs or faculty should look at?
Anomaly detection would be one that we haven't gone big time. We are looking at it. This might be a very interesting area. The other thing is a very challenging problem that we've seen. We've solved this problem at a smaller scale. Is how to crawl graphs in real time. Getting a graph crawler that does real-time crawling at enormous rates. I know that there's this thing called RAM Cloud, and we talked to one of the PhD students from there some time back. I was very interested in solving a graph problem. If you can solve that, I think that will be a great contribution.
Yeah, I think any of these streaming algorithms to detect anomalies, to count top N, to do percentiles. Actually, there's a lot of literature in those, and we are implementing some of those already. But in general, that field is something which is, I think, still lot more work to be done, actually.
So I will actually connect you guys with, there's an individual, Dimitris, who's currently pursuing his postdoc at Berkeley in the AMP lab, which of course is the home of Spark. And he had done his last webinar on sort of streaming dense case subgraphs where the graph has got sort of billions of nodes. And it might actually, the use case he talked about was sort of in a social graph, but obviously anomaly detection might be an interesting thing when you have sort of millions of billions of packets flowing in, etc. So anyway, I'll connect you guys with him because he was interested. I think he dropped off right now, but it'll be interesting for him to talk to you guys. Anyway, I guess I see no further questions, and today I guess we've had quite a few folks. It's right now, I think, 3 a.m. in India. There's a participant from there as well as in China and, Germany and in the U.S. So thank you all for coming. Bhaven, I don't know if you've attended previous webinars. I know Sharad has not, but we have a tradition since obviously it's you guys in a conference room and all of us are worldwide. We have this tradition to sort of, give you guys a virtual applause for a very nice, informative, talk that I think you guys have done in a tremendously busy schedule and so on. So we really appreciate it and, hope that the ideas shared by eBay can spur interesting insights, innovations, and ideas. Feel free to connect with me as well as with Bhaven and Sharad as appropriate. And, if there are any follow-on questions or interactions that need to occur, please let me know. The slides, I think, will be up online. Bhaven, once you send me a copy, I will upload that to the server. And we will be recording this session and putting it up on our YouTube channel. And feel free to share links to that, and hopefully, some interesting breakthroughs along the lines that eBay indicated would be forthcoming from you guys. So with that, let's all unmute our microphones and give me a second to unmute everybody. And let's give Sharad and Bhaven a warm round of applause, please. Thank you. So with that, I guess let's wrap up. We have our next webinar on February 27th when Kunji Zhao from Apple will present a webinar on complex event processing, a paradigm for fast data management. And for all of you who are still around, please sign up for that as well as send in your survey comments so that I can help improve and the seminar. Thank you so much. Talk to you guys later.
Thank you. Thank you.
Thank you.